Two sections left in chapter 5. They're identical except one is derivatives, the other one is integrals of inverse trig functions. This is not fun. A majority of the lesson today is pre-calc review. And I'm sure you rock this in pre-calc, so it'll go quickly. And then, unfortunately, this is one of those lessons where you're just going to end up memorizing the 6 formulas I have for you. Okay, I'll show you where they come from so you can appreciate the derivation, but for the most part, you're going to slap them on note cards and just memorize these things. So we're going to talk about inverse trig functions. What is an inverse trig function? How do you use them to solve problems? Then we'll take the derivative of that thing. Then this marks our completion of all derivative problems now. There are no more techniques to learn after today. So then I've got a nice big honking chart of all the possible ways that you can take a derivative. And then, of course, you should know the presidents from tallest to shortest. Who's the tallest? Abraham Lincoln. Do you know who next? Who's next? Somebody tried to argue that it's Trump now, that he's fairly tall.
He actually is pretty tall.
It's like 6 something?
Yeah.
Really? Yeah.
He looks
Trump
so
is not
small.
6'6".
No, it's
No
not.
way.
No, 6 something, not 6
Hold on,
6.
hold on.
6 something.
What?
I didn't say 6 6. He
No,
just
no.
looks shorter because he has like a little.
What part
like,
of shh didn't you understand?
What?
How tall is Donald Trump?
Checking.
Thank you.
Donald Trump is 6 feet 3 inches tall.
He's not that tall.
I'm
That's
6
pretty
feet.
tall.
That's
It's
tall,
above the
yeah,
average.
that's
I'm
Am I that tall? I'm just.
He's got it.
You're tall. Yeah.
Vince, how tall are you? Do you notice when you're taller than people?
No.
No, but you do notice as soon as somebody bigger than you walks in the room, which probably doesn't happen very often. Yeah, I'm the same way. Like, I don't notice that I'm taller than people, but as soon as
With Alex Palczewski, he's a little bit taller.
tiny,
Yeah,
Yeah.
He's a little bit taller than me, and it's just like when I see him, I think like in my head it thinks like he's like.
just
3
kick him in
inches
the back of
taller
the
than
knee.
me.
Then.
I'm 5'1", so I don't.
Right, but I don't notice that I'm taller than you.
Okay.
But I do notice that he's taller than me.
Alright.
Okay. The trig functions don't have inverse functions, as it says up there. Why? Kevin, are you raising your hand, or are you just deep in thought? Deep in thought. Okay. Good. All right, we'll start calling on some people then. Yuri, why don't the trig functions have inverse functions? What does that mean? Alex, help him out.
Well, you can't really have an inverse because if you take the inverse of one trig function, you just end up with another. So it's not really like a whole nother inverse.
You're thinking too much about it. How do you know if a function has an inverse function? Kidding?
It has to pass the horizontal line test, and if you put a horizontal line through a cosine graph or a sine graph, it will not work.
Good. What about tangent graph?
It still won't work. Wait,
Secant,
it still won't work.
cosecant,
It still won't work.
cotangent.
It doesn't work.
I think I've got them all, right?
Yeah.
Okay, doesn't pass the horizontal line test. That's something you should know. Doesn't pass horizontal line test means it's not 1-to-1. For every x value, there isn't one and only one y value. For every one y value, there isn't only one and only one x value is what I'm trying to spit out. Okay. So what do? The way we get around this is we start restricting the domain now for the trig functions. And this might look a little bit familiar to you. Remember that business? Oh yeah. Yeah. I told you it wouldn't be very fun. Because the sine function, cosine function, all 6 of the trig functions aren't 1-to-1, meaning they don't have inverse functions, we restrict the domain that guarantees that they're going to have inverse functions. You're going to need to know those quadrants, and there's a couple of things that you can do to help remember that. Number one is that every function is in quadrant one. Notice we got quadrant one and running down the front of all of those. Number two, the second function is always going to be where the function is negative. So for instance, if we take a look at the top one, which is sine, I want a quadrant where the sign is positive. I want a quadrant where the sign is negative. Sine is negative in quadrants 3 and 4, so therefore we go with 4. Why 4? Because you'll also notice that there's no quadrant 3's up there. So you can logically process this if you forget it. So for instance, cosine. Cosine is positive in quadrant 1, and we use quadrant 1. Where is cosine negative? Cosine is negative in quadrants 2 and 3, but we never use quadrant 3, so therefore we're stuck in quadrants 1 and 2. The reciprocal functions match the function. So if cosine is restricted to 1 and 2, then the secant is restricted to 1 and 2. Sine is restricted to 1 and 4, therefore the cosecant, which is its reciprocal, is restricted to 1 and 4. And all that makes perfect sense until you get to the tangent and the cotangent, and that screws everything up. Tangent is positive in quadrant 1. Where is the tangent negative? The tangent is negative in either quadrants 2 or 4, so for tangent, we choose to use quadrant 4. It would be nice then if the cotangent was the same, but for some bizarre reason it gets changed to quadrant 2. These are the two that are going to give you major problems there. And this is something you probably just have to remember. Tangent in 1 and 4, cotangent 1 and 2. And there's probably some bizarre mathematical explanation for that, I just don't know what it is. Which means now, when we take an inverse function of a value, we're going to get one and only one number instead of an infinite number of numbers. Because now every x has only one y and every y has only one x. Okay. So for instance, what's the arcsine of negative 1/2? What I'm asking there is, I've got an angle, and when I take the sine of that angle, I get negative pi over 2. Where is that angle? Now, a couple things to remember. We're no longer going 0 to 2 pi. We're now going pi over 2 to negative pi over 2, which means that quadrant 4 goes from 0 to negative pi over 2. So now we have negative angles here. In other words, 11 pi over 6 is no longer 11 pi over 6. It's negative pi over 6. That I already said about finding the angle. And so in that interval from negative pi over 2 to pi over 2, the sine is equal to negative 1/2 at pi over 6. If you never learned the unit circle or you're bad at it, this is going to kill you. You need to know the unit circle inside out. Question?
The arcsine, that's just talking about the arc measure equals the angle, right?
No, arcsine is just a different way of writing inverse.
Oh, okay.
I guess I should have explained that.
'Cause I completely forgot about this.
Arcsine is the same thing of something, whatever, is the same thing as the inverse.
Okay.
Same way to write the same thing. Or different ways to write the same thing.
So when you're finding the arcsine, the negative 1/2 is referring to the angle measure,
No, it's referring to the value.
the value, and then y is the angle measure.
What angle gives me a value of negative 1/2?
Okay, cool. Alright, thank you.
So where's cosine equal to 0?
Pi over 2?
Or,
Negative pi over 2.
which one do we go with? Can't have more than one answer.
Pi over 2.
It is pi over 2. And the reason it's pi over 2 is if we go back to the previous slide, it is restricted to pi over 2 instead of negative pi over 2. So we take the positive value there. Where's tangent equal to square root of 3? Well, tangent is sine over cosine. Excuse me. To get square root of 3, I would get square root of 3 over 2 over 1/2, which means I need a y value that's the square root of 3 over 2. I need an x value, which is at 1/2, and that happens at pi over 3. Outstanding. And the last one, where's the arcsine of point 3? Is point 3 on the unit circle? Nope. So how do I find the arcsine of point 3? Calculator, that's right, bust out your calculators, tell me what the arcsine of point 3 is. I know you've all done this before, just to make sure we're on the same page. The arcsine is above the sine button. second sine of 0.3, and your calculator should be in radians mode. Hold on. Where's your calculator? Bust it out. Let's go. And remember, the AP standard is 3 decimal places, so therefore, Yuri, what's the inverse sine of 0.3? Well, that's a good place for it.
0.35.
Alex, don't do that again. I'm having fun disciplining him, and you just jumped in to save him.
I apologize.
Let him drown. We'll drag the carcass out later. 0.305. Because again, AP standard 3 decimal places. If it's on the unit circle, you're going to stay with an exact answer. If it's not, then you're going to use the calculator. Again, still going with the precalculus. We've talked about this already. You take a function, put it into the inverse, you take an x. You get x, I'm sorry. You put the inverse into the function, you get x. So now we can start combining functions with an arc sine and a sine. And it would seem logical that if I took the arc sine of the sine of something, they would just undo themselves and we'd get the answer. Like taking the square root. I take the square root of a function, then I square it, I end up back where I started. But now we're restricting domain, which means it doesn't always work out. Case in point, what is the sine of pi? Come on. 0. What's the inverse sine of 0? Where does the sine equal 0? Or 0. Which one do we go with? Sine is restricted that you have to go with the 0 and not the pi. That'll pop up quite a bit. So for instance, what is the sine of the arc sine of 1/2? You can go through the process here, but one trick to remember, if that value is in the first quadrant, they do just cancel each other out and you get that answer. That's easy. It's when it's not in the first quadrant that you have to do it the hard way. So for instance, what's the inverse cosine of the cosine of negative pi over 2? What quadrant is negative pi over 2 in? Michael, what quadrant is negative pi over 4 in?
3? No, 4.
4. Therefore, I can't just, it's not just going to cancel itself out and get negative pi over 4. I got to do the work. What's the value of the cosine of negative pi over 4? If you prefer, 45 degrees down.
2.
Are you guys root 2 over 2 people or 1 over root 2 people?
Root 2 over 2.
Root 2 over 2?
Yeah.
I'm a 1 over root 2 person, but that's all right. We can still get along. So the cosine of negative pi over 2 is positive 1 over, well, sorry, root 2 over 2. So what's the inverse cosine of that? Where does that happen? Good. Yeah. Well done. Because we have to take that quadrant 4, which is not in our domain restriction, and we need to force it to come up into quadrant 1 or 2, because that's where the cosine is restricted. What about that? Where is 2/3 on the unit circle? Katie, where's 2/3 on the unit circle? It's not, so what do we do?
Calculator.
No.
No, wait.
I want an exact answer here, not an approximate. When in doubt, draw a triangle.
No.
Draw a triangle for this scenario. Okay. Well, what does that scenario mean? What does that scenario mean? Yeah, that's correct. There's some angle, I called it theta, that when I take the cotangent of that angle, I get 2/3. What is cotangent?
Cosine of the sine.
Okay. Let me rephrase my question. What is cotangent based on opposite, adjacent, and hypotenuse?
Adjacent over opposite.
Good. Adjacent over opposite, which means I'd get that triangle. Here's my angle theta. The adjacent side is 2. The opposite side is 3. The only thing that stuff in the parentheses did is allow me to create that triangle. Now I'm done with the triangle, and now I just want to take the cosecant of that triangle. What's cosecant? let's see, cosecant is the reciprocal of sine, and sine is
Opposite over hypotenuse.
opposite over hypotenuse, so the reciprocal of opposite over hypotenuse is
Hypotenuse over
hypotenuse over opposite. I don't have the hypotenuse. Can I find the hypotenuse? Yeah, what is it? Square root of 13, good. So therefore we get the square root of 13 over 3. Once you build your triangle, you know automatically you're going to have to find all three sides, so at some point you're going to have to do some Pythagorean theorem to find that value. It doesn't matter what this function is out in front. Once I have the triangle, I can answer any one of the 6, because you should know that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent, blah, 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 blah. All 6 of those for each of them. And even if you only know 3, you should know the reciprocal function. In other words, if you don't remember cosecant, you can go through the same thought process that I use to arrive at the cosecant.
So you're being asked to find the outside thing. So you're being asked, okay.
This builds your triangle. That answers the question.
Okay. Yes.
What if there's no numbers?
Right.
Draw that triangle. X is x over 1. Wait a second. Sine of x. X is x over 1. Opposite over hypotenuse. How long is the third side?
Root 1 minus x squared.
Root 1 of the quantity minus,
Yes.
yeah, that.
Yes.
Good. Now that I have that, I've got my triangle done, and I can do any one of the 6 trig functions. This one happens to be cosine. What's the cosine of that angle theta? Cosine is adjacent over hypotenuse, so you would just get that thing. Square root of 1 minus x squared over 1. One last thing for now, solving trig equations. When you're solving an equation, we have a basic rule, and that is whatever you do to one side of the equation, you got to do to both sides. What do I want to do to both sides of the equation to solve this? How do I undo an arctangent? Take the tangent of both sides. What's the tangent of the arctangent of 2x minus 3? Good. What's the tangent of pi over 4? Root 2 over 2, or, you know, I like, wait. Yeah, you said so convincingly I bought it. It's 1. Anybody need help solving this equation? You sure? So you got 3, right? I'm just kidding, it's 2. Thought I could fool you. You guys. All right, we're done with that stuff. We're not done for today. That's all pre-calc. You did all that last year, right?
He's like, it's a fun little review. And then it's
Yeah, I was waiting for the derivative. I'm like, where is it?
It's right here.
Okay.
Once again, I'll warn you, you're not going to like this.
Oh,
really sad when I have to go on to the next page for notes. I just would like to say that.
This is going to make you really sad.
Oh, are you kidding me?
Now hold on, before you write all this down, first of all, it's in the book, so if we don't get to it, that'll be fine. But let me show you where these come from, because I think it's important that I'm not stupid. You're all just going to go memorize these, or you're never going to learn them, and you're going to pray that these problems don't show up. But guess what? They're going to show up. So let's assume you're going to just memorize these. I think it's important that you understand where at least they come from. You're not going to do this ever again after you watch me do one of them. But I want to show you where the derivative of the inverse sine comes from. And all the other 5 are found using the exact same technique. So if I have a function defined as the inverse sine, then like we did when we were solving the problem, I can just take the sine of both sides, and I end up with that. Okay, we good on that step?
Yeah.
Good, because the sine of the inverse sine is just x. And now take the derivative. Oh, there's my triangle, by the way. We might need that later. Then take the derivative implicitly. Using implicit differentiation, what's the derivative of the sine of y?
Cosine of y.
Negative.
Negative cosine of y.
Y prime.
Yeah, good, y prime. But I'm gonna get all fancies in my pantsies and use dy over dx instead of just y prime.
When should we use like dy over dx versus like y prime?
You could have used y prime here. I just did. Anytime you're taking a derivative with respect to x, so most of the time when you would do implicit differentiation, you can use y prime. You can't when you're doing like related rates problems where it's you're taking a derivative with respect to time. Okay? Good. The implication is that y prime is actually with respect to x, so you don't have to write it that way.
Okay.
All right, so just move the cosine over to the other side. And now I know what that is using this puppy. What's the cosine of y? Because remember, y is the angle down there.
Square root of 1 minus x squared.
Good, square root of 1 minus x squared, which gets us to this business. Come on. There we go. This looks a little bit different than the formula I have on the previous slide. Why does it look different? Because the one on the previous slide takes into account taking the derivative of an inverse function of something other than just x. So how do I change it? Well, I turn the x into a u. Easy. And then I have to chain on a du dx. And to make life a little bit simpler, instead of writing du dx after everything, I turned it into a u prime and put it up on top. So if this was u's, I'd change that to a u, I'd put a du dx here, or a u prime, and I just move the u prime up on top. You do that 5 other times, and you have all the trig values under control. And that's what this chart, going backwards, getting there. Come on, almost there. Yep. Should have thought of this ahead of time. There we go. That's where all 6 of those come from. And yes, you need to know all 6 of those. Okay, got them?
Almost.
Almost, okay. Again, if there was ever anything that would be designed for a note card, it would be these 6 things. Okay, little piece of closure here. Question?
You know how you said you have to chain on the derivative of u? Where's that accounted for?
So in the derivation that I did, it was 1 over 1 minus x squared.
Yeah.
So now by sticking a u in there, I would have a du dx or u prime on the end. I just moved it up into the numerator.
Oh, okay.
So it makes the formula a little bit nicer. The only piece of advice I can give you in solving these is you just have to ask yourself, whoops, I went the wrong way. Let me go through this. Okay. What is u? And then once you know what u is, it's literally just a matter of plug and chug. Okay, so for instance, if I'm taking the derivative of the arcsine of 2x, I know that u is 2x. What's u prime? 2. So then u prime over the square root of 1 minus u squared, quantity u squared, done. Simplify, you could write 2x quantity squared as 4x squared. And that's all of these are just examples of those kind of problems. Asking again, what is u? Here, u is e to the 2x. Figure out what du is, put that up on top, and then plug and chug into the formula. Now, what we got is this bad boy. There are 24 of these. This is every derivative technique we've talked about. But some of these are written in such a way that it's confusing. For instance, number 1. What are we doing there? Well, we're just taking the derivative of a function. What is the derivative of 2x cubed? 2 times the derivative of x cubed. Okay? So some of this stuff is so second nature. What's another name for number 3? Product rule. How about number 4? Quotient rule. What did we call number 6? No.
Power.
It's power rule.
Oh.
It's got a little chain rule wrapped up in there, but it's still just the power rule. Well, that's ridiculous. And then all these weird ones. We just did all of these down at the bottom. So really, up until this chapter, we've only focused on 1 through 8. 9 through 24 is all in chapter 5. So there's the log stuff there, there's the e stuff, and then all the trig stuff. So 12 trig functions.
This is like,
Why?
is there like this review thing here on Schoology?
No, but it's in your book on page 378.
Okay.
Okay. Yeah.
I'm gonna
So-
write that number down.
If we're doing like more chapters after this,
Yep.
it's like we're doing like 6 and 7, right? So,
Yep.
like, that's it, right?
Yep.
Okay, so what are 6 and 7 then? If this
Applications.
Is, okay.
Yep.
Am
A
I
couple
gonna-
other weird theorems.
I gotta cry.
Probably at some point.
Okay.
Yes.
You want me to lie to you?
No.
Okay, so yeah, you'll probably cry.
I'm crying.
Tell me that.
So then tomorrow quiz. Friday, when we finish up with 5, 6 and more derivative, 5, 7, when we get to 5, 7, it's this stuff but integrals. And then at the end of 5, 7, I've got a big honking chart of all the integral techniques we've had. And we're pretty much done. We go back and visit a little bit of chapter 6, then we get into chapter 7, which is pretty meaty and scary and nasty, but there's no new techniques there. It's applications. We're going to be finding the volumes of solids. Yeah, it'll be fun. Spinning things around axes and calculating volumes. Laney?
So is the homework for tonight due tomorrow or Friday?
No, tomorrow quiz. 2 Friday.
We
Okay.
have homework today?
Yep. You have day 81.
That's tomorrow's